Good morning, everyone. Let's continue with problems on time response analysis. All right. So, the fifth problem, this is in continuation with the previous class. Fifth problem, let's consider. So, statement is like this. For the system shown below, obtain the response to the unit step function. So, the given system is a closed loop system with unity feedback. So this is the given system. All right. And you're supposed to find the step response, unit step response, right? Fine. So let's try to solve this. So you can take this as g of s and this as h of s, which is 1 for this particular case. So you can determine c of s by r of s, g of s divided by 1 plus g of s into h of s. So g of s is 2s plus 1 by s square divided by 1 plus 2s plus 1 by s square into 1. So you simplify, so you get c of s by r of s is equal to 2s plus 1 in the numerator, and in the denominator you will have s square plus 2s plus 1. Right, so this is your closed loop transfer function. Now, what you have to do is compare this closed loop transfer function with the standard form. So the condition is compare. Okay. So when you compare, you will see that the numerator of standard form is not agreeing with the numerator of the given system's transfer function. Yeah, this is what I was trying to tell you. The given system has a numerator of 2s plus 1, whereas the standard form is having a numerator which is omega n square. So this is independent of s. So in other words, what we can say is that the given system has a 0, right? If you recall, when you equate the numerator polynomial to 0, you get something known as zeros of the system. On the other hand, if you equate the denominator polynomial to 0, you get poles of the system, right? So the denominator polynomial is also called as the characteristic equation. So the characteristic equation, the standard form, is agreeing with the system form, but the numerator is not the same. You have a 0 in your given system. On the other hand, the standard form doesn't have a 0. So you cannot directly apply the unit step response in this case. You need to find out the unit step response c of t, by applying partial fraction method. Okay, we can do that very easily. Now, what is the zeros of this particular system? So to find the zeros of the system, what you have to do is you equate 2s plus 1 to 0, or you would get s is equal to minus 1 by 2. So you have a 0 at minus 0.5 location. So this is your negative real axis and this is your imaginary axis. Okay. So that is the 0 location for this particular system. Okay, and if you equate this to 0, you would get the roots as okay, you can apply the I mean, you can just substitute the calculator and you can find the values of S1 and S2. Okay. So that will give the poles of the system. Fine. Nevertheless, let's continue with the problem. Okay. Discretely, you can find out about that. Okay, fine. So let us write C of S by R of S as 2s plus 1 divided by s square plus 2s plus 1. Okay. And we can write C of S as R of S into the given transfer function 2s plus 1 s square plus 2s plus 1, where R of S is 1 by s, because we are supposed to consider R of S as a unit step function. Correct. So you would get C of S is equal to 2s plus 1 in the numerator, and in the denominator s into s square plus 2s plus 1. Or you can write C of S by R of S as 2s plus 1 divided by s into. So this is s plus 1 the whole square. So s plus 1 the whole square. Alright. Now you can apply partial fraction method. So you can write applying partial fraction method. So I'll write just the right hand side of this equation. So let me write 2s plus 1 divided by s into s plus 1 the whole square as okay, a by s plus b by s plus 1 the whole square plus c divided by s plus 1. So this is my partial fraction method. Whenever I have a factor a plus b the whole square in the denominator, right? Okay. Now you can find out the LCM, and you can find out the values of a, b, and c. All right, fine. So let's take LCM. So let me just take the numerator part, because denominator part will be the same, right, for the LHS term as well as for RHS term. Okay. So first let me take it as it is, then I can show you what I was talking about. Take out the LCM. Denominator, you will get s into s plus 1 the whole square. This is what I was talking about. You will get the same denominator. And in the numerator, you will have a into s plus 1 the whole square plus b into s plus c into, you can say cs into s plus 1. Okay, so this is what you get when you compare the numerators. Now compare the coefficient of numerator. All right. So on the left hand side, you have the numerator as 2s plus 1. Okay. Coefficient of numerator terms, you can say. Numerator terms. Here let us expand. Okay. So you get a into, you get a square plus 2s plus 1 plus bs plus cs square plus cs. Okay. Now what you can do is you can group the s square terms together and s to the power 1 terms together. Okay. So you will be able to compare the coefficient of s terms with LHS terms. All right. So it is 2s plus 1 is equal to I have an s square term here and I have s square term here, right? So put together a plus c the whole square I can take. Sorry, a plus c into s square plus you have 2as, bs and cs. So it is 2a plus b plus c into s. Right? And then finally you have independent of s term a, right? Yeah, that's it. Only a you have, which is independent of s on the right hand side. Now you can start comparing the coefficient of s. Okay, so from s to the power 0 term, okay, that is this s to the power 0, we get a is equal to 1. So you get a is equal to 1. Okay, then probably you can compare s to the power 2 term. Okay, on right hand side you have a plus c, right, which is equal to left hand side. You don't have any s square term on the left hand side, so a plus c is equal to 0, and c is equal to negative a, and a is 1, so c is equal to minus 1. Okay, so having known a value and c value, you will be able to find b value, and this b is associated with s to the power 1 term. So coefficient of s to the power 1 term on RHS is 2a plus b plus c, and on LHS is 2, right? So you can write from s to the power 1, you can write 2 is equal to 2a plus b plus c, or 2 is equal to, okay, a is 2, so 2 plus b minus 1, okay, or b is equal to, you will get it as 1, right? Because this gets cancelled, and when you equate, or if you bring b to the left hand side, you will get it as positive 1. So you have found the values of a, b and c. Let us put it back to the equation. Okay, so next you can write, substitute a, b, c values. Okay, so you would get c of s is equal to a by s, right? So a is 1, so 1 by s, and then you have b by s plus 1 the whole square, so plus b divided by s plus 1 the whole square, plus c divided by s plus 1. So value of c is negative 1, so minus 1 divided by s plus 1. Okay, now this is in standard form basically. So when you apply inverse Laplace transform, you get c of t. So c of t is equal to Laplace inverse of 1 by s plus Laplace inverse of 1 divided by s plus 1 the whole square minus Laplace inverse of 1 divided by s plus 1. Okay, so when you apply the inverse Laplace transform, you would get c of t is equal to inverse Laplace of 1 by s is 1. Okay, it's nothing but unit step function, the steady state part of the output, plus inverse Laplace of 1 by s plus 1 the whole square is t into e to the power minus at. A value is 1, so it is e to the power minus t. Okay, sorry, plus sign, because there is plus sign associated, and then you have the negative term. This is Laplace inverse of 1 divided by s plus 1. So that is e to the power minus at. Again, a is 1 here. So e to the power minus t. So this is your time response against step input. All right. So you can say that this is your steady state part of the output, and these two are the transient term, CTR of the transient. So put together, you get total time response C of t. All right. This is your first problem for the day. Okay. Let's consider a different type. Let's see. Okay, I'll keep the explanation as simple as possible. If you have any feedback, you can drop it in the comment section. Sixth question. Let's take. All right. So the problem statement you take. The system shown below is consisting of a unity feedback system with a minor feedback loop. First one, that's case 1. In the absence of derivative feedback, they have given some coefficient a is equal to 0. So a is equal to 0 signifies that the derivative feedback is absent. Determine the damping ratio and undamped natural frequency. So for first condition, you need to determine undamped frequency omega n and zeta. Okay. Then second case, determine the constant a. Determine the constant a which will increase the damping ratio to 0.7. So determine the damping ratio, determine the value of a which will increase the damping ratio to 0.7. So that's your second part of the question. Third one, find the overshoot in both cases. Find the overshoot for both the cases. All right. So this is the question. So I'm supposed to give you the diagram. So they have given the diagram. Let me draw the diagram. Okay. So this is the system. All right. Now, this is your derivative feedback. Derivative is nothing but differentiation, right? So, what is happening is the output is taken and it is being given to a derivative. Okay. So, differentiation in Laplace domain. So, you have say dx by dt. right? So when you convert it to Laplace domain, so from time domain to Laplace domain you are converting, you will get s into x of s. So this s term, which is present in the feedback loop, simply tells that it's the derivative factor. Okay. So basically you are taking the output and then differentiating it and then feeding back to the reference input. So this is called as derivative feedback control. Okay. So derivative feedback control takes some corrective, it does some corrective action in your system output. Okay. So that is what we are trying to find out. So if you go back to the question, so this question is being divided into three parts. In first part, you are supposed to evaluate the damping ratio as well as the maximum overshoot in the absence of derivative feedback control, right? And in the second part, they are asking us to consider the derivative feedback and asking us to recalculate the overshoot basically. So by doing so, we can appreciate the role of a derivative feedback control in control system. All right. So let's go back to the case number one. That is, set a is equal to 0. That means to say no derivative feedback. Okay. So when you set a is equal to 0, this doesn't come into picture. So you can eliminate the derivative feedback. Hence, through and through signals you will get. So you can eliminate the second summing point as well. All right. Now what you have is a plain g of s with h of s is equal to 1, unity feedback control. So you try to find out c of s by r of s. Okay. So remember, this is for a is equal to 0. That is in the absence of derivative feedback control. So c of s by r of s is equal to, you can just apply g divided by 1 plus gx into 1. So when you simplify, you will get 8 divided by s square plus 2s plus 8. So this is your closed loop transfer function in the absence of derivative feedback. Okay. Once you have this, you can compare. Okay. You can write compare with s square plus 2 zeta omega ns plus omega n square is equal to 0. That is the standard form of the second order function. So when you compare, you get omega n square is equal to 8, or omega n is under root 8. Under root 8 gives 2.83 radian per second. That's fine. You can take it as under root 8. So that's your omega n. And you can also find the damping factor zeta. Okay. So zeta can be found by comparing 2 zeta omega n with the coefficient of s to the power 1, that's 2. So 2 gets cancelled and you will have zeta as 1 by omega n. So 1 by under root 8, or zeta is equal to under root 8 gives 0.3535. Okay. So this is the damping factor. As you can see clearly, in the first case, the damping ratio is very small. It is 0.3535. So you would expect that the system will have a very large overshoot, right? Lesser the damping and greater will be the overshoot. Okay. Let's see. So find the overshoot now for case 1, because in part 3 they are asking us to find out the overshoot. So here itself you can write down overshoot. Okay, MP is equal to e to the power minus pi zeta divided by 1 minus zeta squared into 100. So substitute zeta is equal to 0.3535 and calculate the value of overshoot. Okay, just substitute zeta is equal to 0.3535. Okay. Let's see how much overshoot you are getting. Okay, percentage overshoot. Let's find. Okay. So you will get about 30.5%. So in the absence of derivative feedback, you will get the overshoot as 30.5%. All right. Fine. That's about the first part of the question. So now let's look at the second part of the question. So in the second part, they are asking us to recalculate the overshoot as well as omega n value for a damping ratio with A and with zeta is equal to point, how much is it? 7, right? So 0.7. So you need to recalculate MP as well as omega by considering the derivative feedback control and by considering damping factor of 0.7. So it is being said that determine the constant A, determine the constant A, which will increase the damping to 0.7. So let's see what will happen to MP when the derivative feedback is introduced. Okay, so let's introduce the derivative feedback. Okay, so you'll have to roll back to the original control scheme. So this is your AS. Okay. And try to simplify this block first. So let me call it as, say, G dash of S. Okay, so this particular block, let me call it as G dash of S. So G dash of S is basically E divided by S into S plus 2 divided by 1 plus A divided by S into S plus 2 into the feedback, right? So you have a derivative feedback in your system. So against H of S, you will have AS and you simplify this. So when you simplify, you will get it as S square. This is 2S plus 8S you will get. So yes, if you take common, so you are supposed to get 2 plus 8 here. Okay, so that's the simplification for part 2. Okay. Now the simplified diagram, you can expect it to be in this form. So this is your G dash of S, which is here. Okay. And this is again connected in negative feedback. This is R of S and this is C of S. And for this particular control scheme, you calculate the overall transfer function C of S by R of S. So it is G dash of S divided by 1 plus G dash of S, because H of S is 1. H of S is 1. So you can write it down, E divided by S square plus S into 2 plus 8A divided by 1 plus A divided by S square plus S into 2 plus 8A. Okay. Now you simplify this. So when you simplify, you will get C by R as in the numerator you will have 8, in the denominator you will have s square plus s into 2 plus 8a plus the numerator 8. So this is what you are supposed to get upon simplification. Okay. So this is your transfer function with derivative control. Okay. You can observe that the second term is changed. Without derivative feedback, you have had 2s term, right? Now with the feedback, a term is coming into the picture. All right. Now you compare the new transfer function with the standard form. So compare the characteristic equation. Compare with s square plus 2 zeta omega ns plus omega n square is equal to 0. Okay. So very interesting result we'll get. If you see omega n square, it is still 8. That means to say the derivative feedback will not affect the natural frequency of oscillation, right? So omega n is still under root 8 radian per second. Okay. So it will not change the natural frequency of oscillations, but it does changes the damping ratio, right? Because you get a different term over here. So if you compare, you get 2 zeta omega n is equal to 2 plus 88. Okay. Remember, in case 1, you have had 2 zeta omega n as only 2, but now you are getting 2 zeta omega n as 2 plus 88. Okay. And for our calculation, zeta value is given, that is 0.7, and omega n is also given in the sense you can find out, so that is under root 8. So you can find the value of a. So if you simplify, if you substitute zeta value and omega n value, you will be able to find the derivative factor a. So a value, you will get it as 0.2449. 0.2449. So that is the derivative factor or coefficient. All right. Fine. So that's the first task, to find factor A. Now you can recalculate MP, maximum overshoot. So recalculate MP. So it is minus pi zeta divided by 1 minus zeta square, for zeta is equal to 0.7. So substitute zeta is equal to 0.7 in this relation and find out the value of MP. So when you substitute zeta is equal to 0.7, you will get MP value as 4.59%. MP value as 4.59%. So this problem clearly demonstrates that with the help of derivative feedback, the operator can reduce the maximum overshoot. Without derivative feedback, the overshoot was around 30%. With the help of derivative feedback, the overshoot is reduced from 30% to just 4.59%. So this is a way to reduce the overshoot in control problems. All right. Okay. 7 problem, let's consider. It's a different type of problem. You will understand eventually. It's given that a negative feedback system with unity feedback has a plant g of s is equal to. So negative feedback system with unity feedback is consisting of a plant whose transfer function is this 2 into s plus 8 divided by s into s plus 4. Find the response of the system for a unit step in. So find C of t for unit step input. Second one, part B, is using final value theorem. In short, final value theorem, let me write it as FVT. Determine steady state value of the response. So basically you need to find steady state value. Simply because anyhow steady state output is independent of time, so you need to determine CSS, you can say. All right, for a step input. So this is the question. You need to firstly find out C of t for unit step input, and then you need to find out the steady part of the output by applying final value theorem. Okay, that is when t tends to infinity, what is CSS? This is what you need to find out in part 2. Okay, so since it's a unity feedback system, h of s is equal to 1, so you can find C of s by R of s, which is 2 into s plus 8 divided by s into s plus 4 divided by 1 plus g of s into 1. Okay, so take out the LCM. In the numerator you will have 2 into s plus 8, and in the denominator you will have a square plus 4s plus 2s plus 16, right? So put together you have 2 into s plus 8 in the numerator, and in the denominator s square 6s plus 16. Right. So this is your transfer function. Now if you compare this transfer function with the standard form, you would see that the standard form is not agreeing with the given form, right? If you see carefully, you would see that the standard form is not agreeing with the given transfer function form. That's because the given transfer function has a 0, basically. It has a 0. On the other hand, the standard transfer function is free from the zeros, right? So you have to apply partial fraction method to find C of t. All right. So let's try applying the partial fraction method and let us see what we get. So let me take it as it is. We have C of s by R of s is equal to 2 into s plus 8 divided by a square plus 6s plus 16 plus 16. So that is your closed loop transfer function. and R of s is 1 by s. So C of s, you can write it as and using partial fraction method, you can write it this as a plus s plus bs plus c divided by s square plus 6s plus 16. Okay. So take LCM. You get 2s plus 8 divided by is equal to a square 6s plus 16 plus s into bs plus c divided by the denominator, okay, which is equal to, okay, let me just write 2s plus 8, and in the denominator let me just write the denominator, because on the right hand side as well as on the left hand side denominator remains the same. And let me expand the numerator such that let me collect s terms together, s to the power 1 terms together. Okay. So if I were to keep a square outside, I will get a here and then b square plus b I will get here, right? Plus I will take s term outside, so a into 6, so I will get 6a here, and I have s into 6, so c I will be having it here, and independent of s term is 16 into a. Okay. And when you simplify, okay, if you compare s square terms, so compare s square terms, you find that on LHS there is no s square term, so basically a plus b is equal to 0. Okay, and if you compare s to the power 1 term, you have 2s right here, so coefficient 2 is equal to 6a plus c. So from s to the power 1 you can write 2 is equal to 6a plus c. Alright, and you have from s to the power 0 term, that is independent of s, you can say 2 into 8 is 16 on left hand side, and on right hand side you have 16a, so 16 gets cancelled, so you will get a is equal to 1. If a is equal to 1, your b is negative a, b is negative a, so b is minus 1. And similarly, you can find c value, so c you will get it as minus 4. So a is 1, b is minus 1, and c is minus 4. Okay, so let's substitute these values into the main equation. Okay, so let me substitute the values in the main equation. A is 1, so it is 1 by s. B is minus 1 and C is minus 4. So what I can do, I can take out the negative sign and I can write Bs. So 1 into s, that is s, plus C, right? So I have taken minus sign out, so I can write s plus 4 in the numerator. Alright. So this is my the simplified expression. Now if you see this expression, you cannot apply Laplace inverse as it is, right? It's not so straightforward, because Laplace inverse of 1 by s is 1. which you can write very easily. However, there is no standard formula for this. So, what is the Laplace inverse of s plus 4 divided by s square plus 6s plus 16? I don't know. So, that we are supposed to find out. In order to find the Laplace inverse of second term, what you can do is you can think of converting this non-standard form into a standard form. Okay, so that is what I wanted to discuss in this particular problem. Okay, let's see how exactly we do it. So let us not touch the first term. Let's keep it as 1 by s, because we have a readily available formula for 1 by s minus. Okay, so in the numerator, I will not do any manipulation. I'll keep s plus 4 only. Somehow, if I can bring the form something like s plus a whole square plus some b square, I will be able to directly apply inverse Laplace transform. So, whenever you have the non-standard terms appearing in your output CFS, your first aim is to convert those non-standard quadratic equation into something like this form. So this is very crucial step. This is what you're supposed to do it. Okay. Now, this is nothing but a plus b the whole square formula, right? In our case, element a is yes. So I have s square here. That means to say a square I have here. B square I need, right? So let's see how to get b square. So a plus b the whole square is a square plus b square plus 2a into b. So as of now, we have 2 into a. So a is nothing but s here. So we have 2s here, right? But in your actual equation, what is that you are having? You are having 6s. So you get 6s provided you multiply this equation with 3. So this is something like, manipulation. So this 3 you have to bring in such a way that you get something like a plus a the whole square form. So I hope it is clear, right? You have 2s here and you have 6s here. So in order to get 6s in this equation, you are supposed to multiply with 3. So that 3 will be the manipulating factor. So you see carefully what I am trying to do. What I am trying to do over here is that, let me write s square plus 6s. Since I am introducing 3 here, let me write plus 9. So that I can write this particular quadratic equation as s plus 3 the whole square. Correct. S plus 3 the whole square is s square plus 3 square, which is 9, plus 3 into 2 into s, that is 6s. And on this side, your original factor was 60. Let me subtract with negative 9. By doing so, I'm not going to harm my denominator. But on the other side, I'm able to get a plus b the whole square form, right? Fine. So that's the trick in these problems. Okay. So you need to practice a couple of problems to understand this particular trick. All right. Fine. Now, 16 minus 9 is how much? Is 7, right? So let me rewrite this. So I can write it something like 1 by s minus, see carefully, I have s plus 3 square in the denominator, right? So let me write it first. S plus 3 the whole square in the denominator. Plus I have 7, right? Which is independent of s. So in order to apply the inverse Laplace, I should have something like s plus alpha the whole square plus b square. You have some standard formula based on that way. So I don't want 7 here. I want something like b square, right? So what I can do, I can take under root 7 and let me square it. So if I square under root 7, I'll get under root 7 the whole square, which is nothing but 7, right? And in the numerator, instead of writing s plus 4, let me write it as s plus 3 plus 1. Okay, all right. Classes. Okay. Now, this equation, let me remodify. So, C by C of s is equal to 1 by s. And the first term, second term, let me take it as s plus 3 divided by the denominator, s plus 3 the whole square plus under root 7 the whole square. And let me write this as minus, let me take it as under root 7 into, in the numerator let me bring under root 7. So these two are going to get cancelled out, so no harm done. And in the denominator I can write s plus c the whole square plus under root 7 the whole square. Okay. Now by doing so, I'm going to get the standard form of inverse Laplace transformation. Okay. Now you apply inverse Laplace transformation. So inverse Laplace of C of s is nothing but Laplace inverse of 1 by s minus Laplace inverse of the second term into minus Laplace inverse of the third term. Okay. You see here, if you take out the LCM, you would still get s plus 4 in the numerator, and in the denominator you will have s plus 3 the whole square plus under root 7 the whole square. Now let me apply the inverse Laplace. So Laplace inverse of C of s is C of t, which is equal to inverse Laplace of 1 by s, which is 1, minus Laplace inverse of this function. What is it? It is e to the power minus alpha t, that is minus 3t into cos bt, so under root 7 into t. So that's the inverse Laplace of first factor, minus the constant ratio 1 by root 7 into Laplace inverse of the third term. Okay, so Laplace inverse of third term basically gives sustained oscillation, exponentially decaying sinusoidal oscillation. Envelope is dictated by the exponential term e to the power minus 3t into sine bt. So this is b and this is a. Okay, so sine under root 7 into t. So this is your inverse Laplace. Okay, so that's how we find the Laplace transformation. Okay. And if you want to further simplify, probably you can take e to the power minus 3t term outside, so it is e to the power minus 3t into cos under root 7t plus 1 by root 7 can be written as 0.142. So 1 by root 7 is 0.142 into sine under root 7 into t. So this is my time response. Okay, so this method probably you can use whenever uh, your C of S is not expressed in standard form. So the way to come out of this problem is to convert the non-standard form to a standard form. The moment you have a standard form, what you can do is you can apply the readily available inverse Laplace formula. All right. So that's your first part of the problem, finding out the step response. Hope you have understood this problem. All right. Next up, we have the steady state part of the output. So, what is the what is the steady state part of the output? That is what they have asked you, right? To find out the steady state value, you have to apply FVT, final value theorem. So, just to recall, final value theorem. So, the steady state value, let's say CSS or the final value. Okay, so CSS refers to final value, can be found by applying final value theorem in Laplace domain. That is limit s tends to infinity s into C of s. So basically you can use this formula to find out the final value. So final value is nothing but the steady state value. So this is our final value, which is nothing but the steady state value CSS. SS stands for steady state. So this is equal to limit s tends to infinity s into the C of s, right? So s into you can directly apply C of s. You can apply the non-standard formula, right? You don't have to use sin Vt and cos Vt. So your non-standard form of C of s was, if you quickly go back, you will find that 2 into s plus 8 divided by s into s square plus 6s plus 16, right? So this was your non-standard formula. So yes gets cancelled, and when you extend the limits, what you get is this becomes 0. So in the numerator you have 2 into 0 plus 8. So 2 into 8 you will have it in the numerator, and in the denominator you will have 0 plus 0 plus 16, right? So it is basically 16 by 16. So your final value CSS is 1. Right? So that means to say, as time t tends to infinity, so as time, okay, the understanding in time domain could be something like this. As time t tends to infinity, output C of t becomes 1 when time t tends to infinity. So this is the understanding. So that means to say there may be the transient behavior, right? There may be some transient behavior in the initial course of time, but as the time tends to infinity, the output will find its expected value, which is unity. All right. So this is how we find the steady state value. Now the alternate approach is also there. So alternate approach is something like this. C of t is equal to, you have found that C of t is equal to e to the power minus 3t into cos under root 7 into t plus 0.142, right? 0.142 sine under root 7 into t. Okay, so when you substitute t is equal to infinity, you cannot substitute t is equal to infinity. So probably you can check in your calculator, you can substitute t as some very large number, say some 6, 7, 9, you put it. Okay, so then you check. Okay, what happens is that the exponential value of minus infinity, right? Minus infinity is always 0. So what is happening is you're multiplying 0 with cosine and sine term. So basically you will get c of t is equal to 1. So this is the alternate approach. This is the alternate approach to find c of t. Problem number 8. So it is given as a plotter. Okay, so you have been given with a physical system. Plotter may be represented by the block diagram as shown below. Determine the value of gain that gives a peak overshoot of 4.3%. So determine the value of the gain for NP is equal to 4.32%. Second one, the value of zeta and steady state error, ESS. The value of zeta and steady state error for unit ramp input. Okay. For unit ramp input. So this steady state error you are supposed to find for unit ramp input. All right. And third one, what is the range of k? So k range for 2% error with settling time is equal to 1 second. So this is the information. So you will be given with plotter configuration, okay, the mathematical model of plotter, and you need to determine the following: k for an MP of 4.3% and zeta value, so as the steady state error for unit ramp input, and range of k for 2% steady state error with the settling time is equal to 1 second. All right. So you can copy the plotter block diagram. Okay. So this is the block diagram of plotter. Okay. So first, what you have to do is you have to determine the k value, right, for a overshoot of 4.3%. So first solution, find C of S by R of S. Okay. So simplification of this block gives, this is 1 and this is ks. So output is 1 plus ks. That is something like you have two blocks connected in parallel. So overall transfer function becomes 1 plus ks. So 1 plus ks can be taken as h of s, because 1 plus ks is fed in negative feedback manner with g of s. So this is your G of s. So try finding out C of s by R of s. So you have 100 by s square divided by 1 plus 100 by s square into 1 plus ks. Okay. So that's equal to, so this is the transfer function, 100 by s square plus 100 ks plus 100. Compare it with s square 2 zeta omega ns plus omega n square. So when you compare, what you get is omega n square is equal to 100 or omega n is equal to 10 radian per second. And you will also get 2 zeta omega n is equal to 100k or zeta omega n is equal to 50k, right? Or zeta is equal to 50 by 10 into k, or zeta is equal to 5k. Okay. So zeta value, you will get it as 5k. So if you can find out zeta, you will be able to find the value of k. Now, how to find zeta? So zeta can be found from NP, right? So in the problem statement, it is given that the maximum overshoot is 4.32%, right? So write down, given MP is equal to 4.32% or 0.0432, okay, in terms of factual value, is equal to e to the power minus pi zeta divided by 1 minus zeta square. So you can take out the logarithm on both sides, so natural logarithm on both sides. So what you get is ln of 0.0432 is equal to minus pi zeta divided by 1 minus zeta square. And ln 0.0432 gives minus 3.1419. So this is minus 3.1419, which is equal to minus pi zeta. So negative negative gets cancelled, and you will be able to calculate the zeta value. So solving, we get zeta is equal to 0.707. So that means to say it is 1 divided by root 2. So zeta is 0.707. Therefore, you can find the k value as you have got zeta is equal to 5k, right? So zeta is equal to 5k, or k is equal to zeta by 5, or 0.707 divided by 5, or k is equal to 0.1414. So that's the value of k. So that's about part 1. Now in part 2, you are supposed to find steady state error. You are supposed to find the steady state error. All right. Now recall that to find steady state error, we want to keep our transfer function in OLTF format. That is, we want to have open loop transfer function. So open loop transfer function is nothing but g of s into h of s. So if you have the open loop transfer function, then you will be able to find the steady state error, right? So how will you calculate the open loop transfer function? So to find the open loop transfer function, what you can do is you can slightly modify the given transfer function. Okay, so your given transfer function was something like this, right? So this was 100 by s square. Okay, and you have had a parallel block here. Now what I'm going to do is I'm going to separate out the parts, okay, or the paths. So negative sign was here. Please check it. So what I will do, I will take two separate feedback paths. So this was your lower part, unity, and this was your second part, right? Whose value was k's. K's. And both have been taken from the output C of S. Okay. Now, my idea is to club these two. So when you club these two, you will get some overall G of S. And the lower part, let me take it as H of S, which is 1. So I have my G of S. Okay. And then I will be having my H of S, okay, which is unity feedback. If I can have these two, I will be able to get my open loop transfer function. So first try to find out what is G of S. So G of S can be found by the conventional formula. So this, let me take it as G dash of S, and this, let me take it as H dash of S. So G of S is equal to G dash of S divided by 1 plus G dash of S into H dash of S. Okay. So G of S is 100 by S square divided by 1 plus 100 by S square into Ks. Okay. Or you can get G of S is equal to 100 divided by S into 100K. S into S plus 100K. Okay, so that's my G of S. Okay, fine. Erase this. And you can also write H of S is equal to 1. So therefore G of S into H of S, which is our open loop transfer function, is equal to 100 divided by S into S plus 100K, right? And then you can find the steady state error, okay, ESS for ramp input, unit ramp input. So to find steady state error, you need to determine static error coefficient kV, velocity error coefficient kV, where kV is equal to limit s tends to 0 s into G of S into H of S. So kV is equal to limit s tends to 0 s into G of S into H of S. That's here. 100 divided by s into s plus 100K, right? So yes gets cancelled, and when you extend the limit, so basically you get kV is equal to 100 in the numerator divided by this is 0, so you get 100K, right? So that is reciprocal of K, 1 by K, or 1 by the K value which you had found, 0.2121, something of that kind. Okay, so that's how you find the value of K. Okay, so please substitute the value of K from the previous step, right? So that's how you calculate the steady state error, right? So therefore steady state error is A by kV, which is 1, because unit step input you are considering, unit ramp, I'm sorry, unit ramp function. So A is equal to 1 divided by kV. And kV you have obtained it as 1 by k. So E double S is equal to k, right? So k is 0.24 something. So that's your steady state error for ramping. So third part, okay. Third part, what I will do, I will leave it open, okay. Try to solve the third part on your own, okay. So it's given that in third part, settling time is 1, all right, and steady state error is 2%. So 2% is nothing but 0.02. So probably what you may have to do is you have to use the formula for settling time, that is Ts is equal to 4 by zeta omega n, and probably you'll have to proceed with, because omega n you have, right? So omega n is 10 radian per second in step 1 you have found, and zeta you had obtained it as 0.707. So you can substitute, all these values, and you can try finding out the k value. Yeah, you're not supposed to take zeta as 0.707 because you have to find out the value of k. So try finding it out. Okay. Let's see how you are going to solve this. All right. So that's it for the day. So in tomorrow's class, let's look at some more problems which are slightly different from the problems what we discussed today. All right. Thank you so much.